No solar panels, no wind turbines, no batteries, no grid, just dirt. And yet, that light is on. What you just saw is real. It works right now. It's happening in your backyard, and almost nobody knows it exists. Here's the secret. Living bacteria, billions of them, are already inside the soil beneath your feet, right now, eating, breathing, moving electrons. And if you know how to intercept those electrons, you get electricity, for free, from dirt. The materials cost less than $5. You can build it in under an hour, and it produces real, measurable voltage. This is called a microbial fuel cell, and it is one of the most suppressed, overlooked, and underestimated energy sources on the planet. Stay with me. This isn't fringe science. NASA has studied microbial fuel cells for long-duration space missions, powering sensors using nothing but the biological waste of astronauts. Think about that. The agency that put men on the moon looked at bacteria in dirt and said, this could power spacecraft. In the Netherlands, researchers at Wageningen University have been running living plant-powered electricity systems since 2009, generating power from the roots of ordinary grass, not lab-grown superplants, grass. In the Philippines, rural communities have been experimentally powered by paddy field microbial systems, rice farms doubling as silent, invisible power stations. The Bill and Melinda Gates Foundation has funded microbial energy research for off-grid communities across sub-Saharan Africa. This isn't a fringe idea, it's a quiet revolution that just never made the news. So here's the question nobody asks. If this is real, and it is, why don't we all know about it? Why isn't this in every science classroom? Why isn't your electricity company terrified of it? Simple. You can't put a meter on soil. You can't charge someone for bacteria. You can't patent the ground. The energy industry is built on scarcity, on dependency, on you needing them to flip your lights on. A technology that lets anyone, in any country, any climate, with any soil, generate electricity from the ground beneath their feet, that breaks the model. So it didn't get suppressed exactly, it just didn't get promoted. It wasn't profitable enough to fund. It wasn't centralized enough to control. It wasn't dramatic enough to make headlines. So it sat quietly in academic journals, in university basements, in the hands of a few thousand researchers who knew, until now. You've actually seen the beginning of this before. Remember the lemon battery from school? Stick a copper wire and a zinc nail into a lemon, connect a small LED, light. You probably thought it was a cute party trick. What your teacher didn't tell you is that the lemon was never the power source. The chemical reaction between the metals and the acid as a conductor was generating a flow of electrons. Now imagine what if instead of citric acid in a lemon, you used the organic acids naturally produced by millions of bacteria living in the soil. Same principle, massively more powerful, endlessly self-renewing. The lemon dies, the bacteria don't. That's the difference between a trick and a technology. Let me break this down in the simplest way possible. Inside soil, especially rich, organic, moist soil, there are bacteria called exoelectrogens. Exotic name, simple function. These bacteria eat organic matter, dead leaves, decaying roots, compost, and when they digest it, they release electrons as a byproduct. Normally, those electrons just disappear into the ground, wasted. But if you place a conductive material, like a carbon rod, a graphite pencil, a copper plate, inside that soil, the bacteria use it as an electrode. They dump their electrons onto it. Those electrons then travel through a wire, just like in any circuit, to the surface, where they can power a load, a light, a sensor, a small radio. Then the electrons return through a second electrode, completing the circuit. That's it. Bacteria eat, bacteria breathe, electrons flow, you get power. No combustion, no fuel, no waste, no noise. Just life doing what life does and you intercepting the energy it produces. All right, here's how you build one. Here's what you need: a container, a bucket, a plastic tub, even a large pot. Rich organic soil, garden soil, compost-heavy dirt, paddy soil if you have it. 2 electrodes, carbon rods from old zinc-carbon batteries or graphite pencils with the wood removed work perfectly. Copper wire, a small LED or a multimeter to read voltage, and optionally, a small capacitor to store charge between pulses. Total cost, under $5, probably less. Step 1. Prepare your soil. You want dark, moist, organic-rich soil. The darker, the better. It means more decomposed organic material, more food for bacteria, more electron production. Pack it tightly into your container. Leave a few inches at the top. Pro tip: add a small amount of compost or coffee grounds. Bacteria love it. Step 2. Place your anode deep. Your anode is the electrode buried at the bottom. This is where bacteria deposit electrons. Push your carbon rod down into the bottom third of the soil. The deeper, the better. That's where anaerobic bacteria live, the ones most active in producing electrons. Connect a wire to this electrode. Run it out of the soil. Step 3. Place your cathode near the surface. Your cathode goes close to the top, near the air. Oxygen at the surface allows the returning electrons to be absorbed, completing the circuit. Connect a wire to this electrode too. Step 4. Complete the circuit. Connect both wires to your LED or multimeter. Now, wait. Give it 30 minutes, sometimes an hour. The bacteria need to colonize the anode, to discover it, to start using it. And then, the needle starts to move. 0.2 volts, 0.4. Sometimes with great soil and deep electrodes, you'll see 0.7, 0.8. The LED flickers, and then it holds, steady, from dirt. Now here's where most people fail. Mistake number 1, using dry soil. This kills it immediately. Bacteria need moisture to move electrons. If your soil dries out, the system dies. Keep it damp, not flooded, damp. Mistake number 2, using metal rods instead of carbon. Steel nails corrode, copper oxidizes. Carbon and graphite don't. They're biologically neutral. Use carbon rods, graphite pencils, activated charcoal plates if you want to go advanced. Mistake number 3, giving up too early. The most common mistake. People build it, check it after 5 minutes, see 0.1 volts, and call it fake. Microbial biofilms take time to form on the electrode surface. This is a living system. Give it 12 to 24 hours before you judge it. Mistake number 4, not connecting cells in series. One cell produces 0.3 to 0.8 volts. To power anything useful, you need to connect multiple cells in series, just like stacking batteries, to add up the voltage. 5 cells gives you 1.5 to 4 volts, easily enough to power small sensors, LED arrays, or trickle charge a capacitor. A single soil microbial fuel cell powers an LED. But what happens when you scale? In controlled research environments, arrays of microbial fuel cells have powered wireless soil sensors continuously for over 2 years, without ever being recharged. The soil powered the sensor that monitored the soil, a self-sustaining system. In Bangladesh, experimental setups in rice paddies have powered small irrigation monitoring devices. No grid, no solar, just the paddy floor. Scale it to a garden plot, a 4x4 array of buried settles, and you have enough power to run a small weather station, a GPS tracker, or a perpetual soil health monitor. Scale it to a field, and researchers start talking about powering entire rural sensor networks. The bacteria never stop. They don't need sunlight. They work at night, in winter, underground. No other renewable energy source does that. I know what some of you are thinking. Is this safe? Yes, completely. The bacteria involved are naturally occurring soil microbes, the same ones in your garden, your potted plant, your compost bin. You're not creating anything dangerous. You're harvesting what's already there. But the voltage is so low, is this even useful? Right now, for most people, this is a proof of concept, a gateway to understanding. But researchers are actively engineering high-output microbial strains and optimized electrode materials that push this into genuinely useful power ranges. We're at the 1890s of microbial electricity. This is the Wright brothers stage. What you build today in your garden is the beginning of something much, much larger. Here's where it gets strange. In 1938, German archaeologist Wilhelm Koenig discovered a series of clay jars near Baghdad, dated to around 250 BCE. Inside each jar, a copper cylinder, an iron rod, residue consistent with an acidic liquid. When reconstructed and filled with grape juice, the natural acid, they produced voltage. The Baghdad batteries. 2,000 years before Alessandro Volta invented the battery. Nobody knows exactly what they were used for. Electroplating, maybe. Ritual objects, some say. But here's the point. The knowledge of electricity from chemistry, from organic material, from the earth itself, is older than we've been told. It didn't start in a European laboratory in 1800. It may have started in the ground. Exactly where we're returning to now. We live in a world that charges us for energy. We pay for the light in our rooms. We pay for the warmth in our homes. We pay monthly for the right to be part of modern civilization. And underneath all of it, beneath every city, every suburb, every empty field, is a living system, constantly producing energy for free. Without asking. The Earth has been generating electricity since the first microbe evolved 3.5 billion years ago. We just forgot to look down. Or maybe we were never really encouraged to. There's something deeply human about rediscovering this, about sticking two rods into the ground and watching a light turn on. It doesn't just produce voltage, it produces a question. What else do we already have that we've been convinced we need to buy? If this changed the way you see the ground beneath your feet, if this made you question even one thing you've been told about energy, about dependency, about what's possible, then share this. Not because of an algorithm, but because someone you know deserves to see it. Build one, try it, fail the first time, adjust, and try again. And when that LED lights up, from nothing but dirt and life, remember this moment, because that's not just electricity.